discussing about the radiative transitions that occur when we have an electron in some lower energy state, and when we supply some external energy to this electron makes a transition to higher order energy levels. And at the same time, this electron can de-excite and emit out the radiation that it has obtained. So the phenomenon in which we have a transition of this electron from say ground state to some higher energy state. This is what's called as absorption, and and for this electron does not stay in the excited state straight. It stays there for a very short span of time, of the order of 10 to the power of minus 8 seconds, and de-excites and comes back to its ground state, and while coming back, it emits radiation. And then we have another category here, which is the stimulated emission of radiation, where we already have an electron in an excited state, and the photon is supplied in such a way to moderate the transition of this electron, which is in a higher energy state. And this phenomenon leads to have photons in phase, and becomes the basic principle for the laser action. Now, what is important here is that we can semi-classically demonstrate, we can semi-quantum mechanically, I should rather say, we can describe the phenomenon of absorption of energy, and the phenomenon of and the stimulated emission of energy. But what seems to be happening in all the domains around us is this spontaneous process, and 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 and, and semi quantum mechanical treatment is not enough to explain this phenomenon of having this spontaneous emission, because the spontaneous emission can take place even in the absence of the external radiations. So to account for the complete explanation of the absorption and spontaneous emission and the stimulated emission, all of these three phenomena can be explained using field quantization, the quantization of electromagnetic fields. So in this video, we will be discussing So now we'll be proceeding in this video for making use of, for applying this quantized field to understand the spontaneous emission. I mean, if we have two states, and we have an electron in an excited state, in absence of electromagnetic energy, this electron makes a transition to the ground state, and semi quantum mechanical approach does not have any answer to this phenomenon, because the transition takes place even in the absence of the electromagnetic radiations, and while coming down, this electron releases the quantum of energy. So what is important here is that we can understand this spontaneous emission problem exactly by quantizing the field, and this transition naturally comes out as a result of quantizing the electromagnetic field. Now, if I assume that we have the electron's initial state is state 2, this is the upper state, and there are no photons in any mode available in this state, and now what we can do is we can write the initial state, the initial state NFS and NBS. So we have an initial state with the fermion, and in this state there is absence of any boson. So we can define this state as B2 dagger 0. So
this B2 dagger is the it's the creation operator. It's the fermionic creation operator. With the energy, if I assume that this state has an energy E2 and this state has an energy E1, and this state has the energy, the state that we have started with, this state has an energy equal to E2. And again, I'm trying to put some lay some emphasis here that that semi-classically uh, uh, we with no electromagnetic field, there's not going to be any transition from the state 2 to the state 1. So the semi quantum mechanical treatment has no answer for this problem, that in absence of the electromagnetic radiation, why this electron has a transition from the upper state to the lower state. So conventionally we'll move from here. So what we'll be looking for is the Hamiltonian uh, uh, operator HP for this state NFS and NBS with this perturbing Hamiltonian, which is basically HED, the Hamiltonian of the electric dipole. This would be written as H electric dipole lambda J and K, BJ dagger BK times A lambda minus A lambda dagger. So we have this Hamiltonian which is quantized. This perturbing Hamiltonian is quantized, and what it is composed of is we have the creation operators for fermions and annihilation operators, and we have creation operator for boson and the annihilation operator for the boson. And uh, and with our understanding, what our understanding is, it starts from this state. We have a vacuum state, a state 0, where we have an electron, and we can uh, we have to start it from this state. The origin of this transition is from this from this state. Now, talking about what we encounter here is the string of these operators in the Hamiltonian, in the quantized Hamiltonian. So we would like to enforce these operators and move on from here. So we can write down Bj dagger Bk times A lambda minus A lambda dagger B2 dagger and 0. So what we can do is we can transfer this B2 dagger to this point. So this is Bj dagger Bk and B2 dagger times A lambda minus A lambda dagger. All right, so we can look for this BK and B2 dagger. Now we have an understanding that that for fermions what we have is they anti-commute with each other. So if I have to write down the anti-commutation relation between BK and B2 dagger, what am I going to write for this is simply delta 2K minus B2 dagger and BK. Yeah. So we can obtain it using the commutation. If we start with this BK and B2 dagger, so since they anti-commute, and we can write down here BK and B2 dagger plus B2 dagger BK must be equal to delta 2K. So from here, we will have this result. So we can write down here BJ dagger times delta 2K minus B2 dagger and BK. Okay, multiplying this with A lambda minus A lambda dagger. All right. So, so what is important here is that we will explicitly we will not use those operators which are acting as annihilating operators, because in our state, B2 state, there is not any presence of any kind of photon. So if that's the case, then we can boil down this equation to minus delta 2k and bj dagger and a lambda dagger and 0. So this is the state that will exist, and the annihilation operator a lambda will be equal to 0, and the annihilation operator bk will also be equal to 0. So what we have here is we have encountered the string operators here, and finally we have reached to this result. Now with this string operators that we have obtained here, we can write down them. Where from we started. We started from bj dagger bk times a lambda minus a lambda dagger times b2 dagger 0, and what we have obtained is minus delta 2k bj dagger and a lambda dagger with the same vacuum state. So what is important here is that if we write down the matrix element for this Hamiltonian, I mean, if I write down the state NFQ, Q being the final state, NBQ, HP, and NF, S, and NBS. So Q is my final state, and this NFS and BS is my initial state. So what is important here is that we have to choose this Q. What is this Q is a point of contention here. So so therefore, I would like to write down the state here as NFQ, and NBQ is BJ dagger a lambda dagger with the 0 state. So what is important here is that the electron is now in some state J, and the photon has some mode lambda. So electron is in state J, and the photon has a mode lambda. Now the point is that we have to establish this J. Now this Q state, which is the final state predefined for this problem, this Q state has the energy. I mean, the Q state has energy. What should be that? That is EQ is EJ plus H cross omega lambda. It has to go like this. All right. So so what we do now is we put this state Q, which has some specific choice involved in it, the choice mode of lambda, and the state, the final state of this electron, which is predefined as J. And what we'd like to do with this state Q is we would like to exonerate it into our general perturbation theory expression. So I would like to write down the perturbation theory expression here, CQ, because Q is the final state, dot with first order as 1 by IH cross sigma Cm0 exp times minus I Em minus En T by H cross, and I'd like to put the brackets here, and the matrix element NFQ and NBQ, HP, and NFM and BM. So so we can write down this equation as CQ dot 1 is It's nearly 1 by IH cross EXP I times EJ minus E2 plus H cross omega lambda T by H cross. And then we will have sigma of the Hamiltonian HED lambda J and K states, and then we will have delta K2 that we have obtained, and the matrix element as 0, a lambda, then bj, and a j dagger, and b lambda dagger. So the value of this matrix is equal to 0. And finally, we come up with the expression for the amplitude here. What is that? That is CQ dot 1. This comes out to be 1 by IH cross EXP iota times EJ minus E2, then plus H cross omega lambda times T by H cross and HET lambda J and 2. So, so this will be our final equation for this expression that we have here. So what we'd like to do is we would like to integrate this equation. So integrating. So on integrating this equation, what we will have is we will have this CQ 1, that will be 1 by IH cross EXP times I times EJ minus E2 plus H cross omega lambda times T by H cross and the H ET lambda J2. And then taking the amplitude, I mean taking the square of this amplitude, we will be able to calculate the transition rate. And the transition rate that we obtain, say WQ, which is basically the Fermi golden rule, will be 2 pi by H cross times HED lambda J2 square and the delta function, as was obtained in case of absorption, EJ minus E2 plus H cross omega lambda. Now, the only possible choice for any kind of transition that we have here is the final state, that is J is equal to 1. I mean, if there is to be any kind of transition that we can expect, then this transition should take place to the state J equal to 1. And if there is to be any kind of transition, otherwise there won't be any kind of transition available. So what will be the requirement of that is that this E2 minus, so this J has to be this J has to be 1 if this E2 minus E1 should be equal to H cross omega lambda. So that's what we have is we have the transition process here. So the transition process is purely dependent. I mean, the transition will take only to the state J is equal to 1. For all other states, I mean, if this EJ is equal to 2, this delta function is going to vanish. So the whole transition rate will be equal to 0. But this delta function will exist for only J is equal to 1. So what we are obtaining here is that we have the state 2. There's not any presence of any kind of photon over there. We have an electron here, and the transition process happens. I mean, the transition, this electron has the only final state as the state 1. And this transition process is basically the spontaneous emission, and the electron starts in the higher state too. It starts in the higher state too with no photons present. There's not any photon present with this electron in this state too, and this electron ends in the state 1 with one photon present with the electron. So what we have here is we have a transition, and we have one photon that is available in some mode, say lambda, and the electron has a transition to the state 1 with one photon available to this electron. So this photon can be in any mode, say lambda here, with the correct photon energy to match the energy separation between the two levels, and for which this Hamiltonian HED lambda lambda 1 2 is not zero. It's not zero. And this process, we can see what has happened here is that this process has emerged naturally as a consequence of quantizing the electromagnetic radiation. Quantizing the electromagnetic radiation. uh, uh, and requiring essentially having no additional physics except quantization of field, quantization of electromagnetic field.